We present lightweight portrait matting via regional attention and refinement. Our goal is a fully automatic system that can predict portrait matting from very high resolution inputs, such as HD and 4K, while at the same time make it run at real time. Because we want the system to be fully automatic, we disallow any auxiliary inputs, such as trimaps and additional background captures, which require user interaction and have been widely used in many existing methods. Also, since we aim at HD and 4K input, which requires significantly more compute budget, this poses another challenge for us. Our method is based on the two-stage framework. The main idea is to estimate a coarse alpha in the first stage, followed by a local refinement. This saves lots of computation because we reuse the coarse prediction from the inner region and only need to refine locations around the uncertain boundaries. As shown in this diagram, we start with a very high resolution input, downsample it by 8 or 16 times to obtain the coarse input. Then we estimate the coarse alpha from the coarse input. Next, we extract local patches around the boundaries and use a second network for refinement. The two-stage framework was originally proposed by BGMV2. In their approach, they used an additional background capture without a human subject as their auxiliary input. We found its performance degrade significantly if we remove the auxiliary input, so we make a couple of changes and improvements. In this slide, we explain our design choices for our coarse estimation architecture. Intuitively, if we do less aggressive downsampling, the coarse prediction will be more accurate, hence the final refined prediction. This can be verified by A and B in the table. When we use a downsampling rate of 2, the results are better than the model using a downsampling rate of 4. However, smaller downsampling rate means more computation, which is unacceptable if our input is HD or 4K. Therefore, we went on with a pixel unshuffle, which divides the input image to non-overlapping patches and move the patch's spatial dimensions to the channel dimension. Compared to downsampling, this reduces spatial resolution but retains more input information. Intuitively, pixel unshuffle should give us better results than downsampling. However, as shown in A and C in the table below, pixel unshuffle with a patch size of 4 is no better than the 4 times downsampling. This is because CNN doesn't work well with large kernels. In this experiment, we use ResNet50 as the coarse estimation network. The kernel size of the first convolutional layer is 7. When we use patch size of 4 for pixel unshuffle, the effective input kernel size becomes 28, which is too large for CNN to work properly. So CNN is not an ideal architecture for this purpose. Then what do? We actually turn to Vision Transformer, or VIT, because the image tokenization step in VIT is equivalently pixel unshuffle. So VIT is a natural fit for our task. As you can see in the table, Model D using Swing Transformer outperforms other models while achieves significantly more reduction in input resolution and computation. In the first stage, we also predict a coarse trimap in addition to the coarse alpha. The trimap divides image space into 3 categories: definite foreground, shown as red in the lower left figure, definite background, shown as blue in the figure, and uncertain region, shown as green in the figure, which is mostly the boundary locations. Imagine that our coarse input is 8 times smaller than the original input for both height and width. We select all uncertain locations from the coarse trend map and retrieve the corresponding 8 by 8 patches from the original input and upsampled coarse alpha. These 8x8 patches with RGBA values are the input to our refinement network. This is a very naive implementation of the refinement network. However, the downside of this implementation is that we lose contextual information. The patches to be refined are individual and have no reliance on each other. Therefore, we propose cross-region attention, or CRA, which applies attention across the input patches to collect global contextual information from them. The most intuitive way to apply attention across all patches is pairwise attention. However, this is very computation expensive because normally we end up with thousands of patches to be refined. To mitigate this issue, we propose KN attention, which applies attention only with the k nearest patches. We found that setting k to a very small value, such as 8, already works pretty well. Also note that our patches are unordered. Feeding them to the attention module without any positional encoding gives suboptimal results. Therefore, we introduce a scheme to encode the relative positions across patches. Our relative positional encoding starts with the predefined search range S on a regular grid. With the search range, we can locate a square window around each patch and create a table whose size is the window area size plus 1. All entries in the table encode the position that are within the window, except the last one, which encodes positions outside the window. Let's use a toy example for illustration. In the figure on the right, we use search range of 3, so we end up with a 5x5 square window. For the yellow patch in the window, its position tells us the corresponding table index is 6, so we assign the table value from index 6 to this patch as its relative positional encoding. This encoding value is used as the positional bias B in the softmax attention formula. Similarly, the purple patches also need to be assigned a positional bias because they are outside the window. We assign the last table value to them to indicate that they are out of range positions. Here we show some qualitative results on high-resolution, high-quality in-the-wild photography images. Existing methods occasionally produce artifacts and false predictions. However, our method is more robust and gives more accurate alpha estimation. Here's a demo video of our model running on an HD input. Our model is temporally stable and produces very sharp boundaries, even on hair strings. We also compared our model with existing state-of-the-art methods on two benchmark datasets, P3M and PPM. Note that unlike all other models, which do not use any auxiliary inputs, DIM uses an additional trimap as input as guidance. That's why it has really good numbers. We include DIM here just for reference, because it's one of the most common baseline used in the community. As can be seen from the tables, our model outperforms other methods on almost all metrics and sets the new state of the art. We also profiled our model on HD and 4K inputs and compared it with other baselines. As you can see from the table, our model achieves the highest frame rate and smallest flops. In conclusion, we proposed a lightweight portrait matting model which runs real-time on high-resolution inputs such as HD and 4K. Our model sets the new state-of-the-art while uses the least amount of computation. That's all. Thank you for watching. For more information, please refer to our poster session and online GitHub.